Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
Welcome, everyone. Today, we're going to unpack an absolutely elegant solution to a notoriously tricky programming problem in this visual explainer. You know, if you've ever stared at a grid of data, maybe you're working with an image or programming a game board, and you've tried to figure out how to rotate that entire thing purely through code, well, you know exactly how fast the math can get completely out of hand. But don't worry, because today, we're going to completely demystify it. Before we even think about looking at pseudocode, we really have to wrap our heads around the core concept. The true beauty of this algorithm is that it bypasses all those messy index rotation formulas entirely. How? By breaking the whole problem down into two distinct, highly logical phases. Honestly, once you grasp this underlying logic visually, writing the actual code is literally just a matter of translation. So here's our roadmap for this explainer. We'll start with a matrix challenge itself, move into the universal logic, break down step 1, which is the transpose, and step 2, reversing the rows. Then we'll look at the pseudocode. And finally, we'll prove it all works with a visual dry run. All right, let's kick things off with a matrix rotation challenge. Visualizing our end goal here is actually surprisingly easy. Imagine a square grid, right? Kind of like the face of a Rubik's Cube. Rotating it 90 degrees clockwise simply means that the very top row seamlessly swings over to become the rightmost column. And conversely, the bottom row hinges up to become the leftmost column. In our heads, it's just a simple, fluid twist. But getting a computer to do that? Yeah, that is where things historically get incredibly messy. If you try to just brute force this by writing out mathematical formulas to track every single grid coordinate simultaneously, like trying to perfectly map out exactly where row 0, column 0 goes, while simultaneously swapping it with row 0, column n, and so on, it is a recipe for massive cognitive overload. You basically end up with these highly complex index rotation formulas that are frankly incredibly difficult to read and even harder to debug when they inevitably break. So, let's step away from the math and look at the universal logic. Here is the crucial takeaway. We absolutely do not need a massive, convoluted mathematical formula for this. We can achieve a perfect 90-degree clockwise rotation using just these two simple, highly logical steps. Step 1, transpose the matrix. Step 2, reverse each row horizontally. That's it. That is the entire algorithm. If you can confidently perform those two fundamental operations, you can rotate literally any square grid. Let's zoom in on step 1, the transpose. A transpose operation essentially asks us to take our grid and flip it completely over its main diagonal axis. Just imagine drawing a straight line from the top left corner of your grid all the way down to the bottom right corner. By flipping our data across this imaginary diagonal line, we effectively turn all of our rows into columns and all of our columns into rows. It's like a mirror reflection across that axis. To actually execute this in our code, we just run a standard nested loop. But the real trick here is that the inner loop starts at I, which represents that diagonal line we just talked about. From there, we simply swap the value sitting at matrix I, j with the value at matrix j, I. It is just a beautifully symmetrical exchange of coordinates. Okay, moving right along to step 2, reverse rows. So now that we have successfully transposed the matrix, our original rows have officially become our columns. The grid is reoriented, but if you look at it, it's essentially mirrored backward. To fix this and finalize that 90-degree rotation, all we need to do is flip each individual row horizontally, straight from left to right. To execute this horizontal flip efficiently, we are going to use a classic two-pointer technique. For every single row in the matrix, we take a left pointer and plop it at the very start, so index 0. Then we place the right pointer at the exact opposite end of that same row. We swap the values those pointers are looking at, and then we just step them inward toward each other. The left pointer moves up 1, the right pointer moves down 1, until they finally meet in the middle. We just repeat this simple swap while the left pointer is strictly less than the right pointer. Let's see how this all translates into our algorithm pseudocode. When we look at the pseudocode for this entire operation, it is incredibly clean, right? For the transpose in step 1, we use a nested for loop, just making sure that our inner loop j starts at I so it flips across the diagonal. Then, for step 2, we use a second for loop to iterate through each row, and we nest a really simple while loop inside that to step our left and right pointers inward until they meet. The logic practically writes itself. All right, now for the fun part. Let's prove it with a visual dry run. Let's start with a really straightforward input to keep things simple. A basic 3x3 grid populated sequentially with the numbers 1 through 9. So row 0 holds 1, 2, 3, row 1 holds 4, 5, 6, and row 2 holds 7, 8, 9. Try to keep this starting picture clearly in your mind for a second. Okay, here is that exact same grid immediately after running our step 1 transpose logic. Remember, we flipped everything across that main diagonal. Notice how the diagonal numbers themselves, the 1, the 5, and the 9, they stayed exactly where they were. But look at the rest of the grid. Our original top row of 1, 2, 3 is now the very first column reading straight down. The grid has morphed completely, so that row 0 is now 1, 4, 7. Our rows have officially become columns. Next up, we trigger step 2, our horizontal row reversal. Look really closely at our new row 0, which currently sits at 1, 4, 7. We place our left pointer on the 1 and our right pointer on the 7, and swap them. The pointers then move inward, pointing together at the 4, which just stays put. So the row is perfectly reversed to 7, 4, 1. Now, applying that exact same left and right pointer logic to the remaining rows, we watch row 1 transform from 2, 5, 8 into 8, 5, 2. And finally, row 2 flips from 3, 6, 9 straight into 9, 6, 3. Look at the rightmost column now. It's 1, 2, 3. That was our original top row. We have achieved a totally flawless 90-degree clockwise rotation, and we did it utilizing just 2 highly predictable, purely logical operations. No crazy math required. I want to leave you with a thought to really spark your coding curiosity as we wrap up this explainer. You now know for a fact that transposing and reversing rows gets you 90 degrees clockwise. But once you truly understand this universal logic, how far can you push the algorithm? Seriously, how would you modify or maybe rearrange these exact logical tricks to achieve a full 180-degree rotation? Take that question with you to the keyboard and keep exploring.
Now let's see how the code looks in C. In Java, In Python, let's now move to the second one.
Hey everyone, welcome to This Explainer. Today, we are diving into the highly visual and honestly just incredibly satisfying mechanics of the famous spiral matrix algorithm. If you've ever looked at a two-dimensional grid of data and thought, how on earth do I programmatically navigate this thing like a coiled snake? Well, you're in exactly the right place. We're going to take the core concepts from our source material and translate them directly into visual steps so this whole logic becomes crystal clear. To make this efficient, we're breaking our journey down into a really structured three-phase roadmap. First, the definition and core concept, then the step-by-step algorithm, and finally a full matrix dry run execution.
All right, let's jump right into Phase 1, definition and core concept.
So, what does spirally printing actually mean in practice? Well, simply put, it means taking a grid and winding around it clockwise. You start from the very outside edge and just keep moving all the way into the absolute center point. Think of it kind of like peeling an apple in one long, continuous strip. That winding, unbroken path, that is exactly what we're programming our computer to do here. Now, instead of getting bogged down in confusing math or grid coordinates right out of the gate, I want you to use a really powerful physical metaphor from our source material. Imagine 4 dynamic boundary walls, top, bottom, left, and right, and they're closing in on the numbers, literally like a trash compactor. To pull off this compactor effect, we actually have 2 distinct actions happening at the exact same time. First, we print the wall, which just means we traverse the outer boundary elements. Then, we physically push that boundary line inward. We're shrinking the box after every single pass. And by doing this, we systematically force our loops into a perfect winding spiral path until those walls eventually just cross right over each other. Okay, Phase 2, the step-by-step algorithm. Let's actually build this thing. We kick off the algorithm by initializing our boundaries. We basically set our 4 walls at the absolute outer edges of the matrix. So the top is at index 0, the bottom is at the total rows -1, left is 0, and right is the total columns -1. Then we set up our master loop, and this loop is going to run continuously, as long as the top wall hasn't crossed the bottom wall and the left wall hasn't crossed the right wall. Make sense? Inside that main loop is where the magic happens. It's a rhythmic 4-step cycle. First, we move from left to right along the top wall, and then push that top wall down. Second, we move top to bottom down the right wall and push it left. Third, we move right to left along the bottom and push it up. And finally, fourth, we move bottom to top up the left wall and push it right. Let's look at the pseudocode and see how this builds out sequentially. Step 1 handles our top row. We run a for loop where an index j goes from our current left boundary over to our right boundary, printing the elements as we go. Once that entire top row is printed, we increment the top boundary, top plus plus. This essentially crosses out that row and physically pushes our conceptual ceiling down by 1 notch. Next up is step 2. We drop from our new top down to the bottom, along that rightmost side. Here, our row index I changes, while our column stays totally fixed at the right boundary. We print as we drop. Once we hit that bottom corner, we decrement our right boundary, right minus minus, which shrinks our compactor box further to the left. Now for step 3, we have a really critical safety check. As long as our top and bottom walls haven't already crossed each other, we run a loop from right to left across the bottom row. After we finish printing that bottom floor, we decrement the bottom boundary with a bottom minus minus. What does that do? It pushes the floor upwards. Finally, step 4. Very similar to the last step, we do another safety check. If the left and right walls are still valid and haven't crossed, we loop from the bottom all the way up to the top along the left column. We print those elements, and upon reaching the top, we increment the left boundary with left plus plus. And just like that, we've successfully completed one full continuous spiral rotation.
Moving into phase 3, matrix dry run execution. Let's see this in action.
All right, here is our starting grid. It's a perfect 3x3 square populated with the numbers 1 through 9. Our dynamic boundary walls are sitting at the absolute edges, so indices go from 0 to 2. Top is 0, bottom is 2, left is 0, and right is 2. The master loop condition checks. Is top less than or equal to bottom? Yes. Is left less than or equal to right? Yes. The engine starts. Let's watch the action unfold. Our first move right loops along row 0. We print the numbers 1, 2, and 3. Because that row is now fully processed, boom, we push the top wall down. Our top variable increments from index 0 and becomes 1. Maintaining that steady rhythm, step 2 kicks in. We move down the current right wall at column 2. Now, notice we skip the 3 because our top boundary is already at index 1, right? So we start there, printing the 6 and then the 9 at the bottom. Once done, the right wall shrinks inward, updating from 2 down to 1. Now we hit step 3. We check if top is still less than or equal to bottom. It sure is. So moving right to left along our current bottom row at index 2, we print the numbers 8 and then 7. Then we push that bottom wall up. Our bottom variable updates from 2 to 1. Completing our first full lap, we do our final safety check for step 4. Left is still less than or equal to right. So we move up the left side, column 0. The only number left between our bottom and top boundaries here is the number 4, so we print it out. The left boundary then shrinks inward, updating from 0 to 1. Okay, now the master loop starts its second pass, but look at this. Top, bottom, left, and right are all exactly equal to 1. The walls are so incredibly tight now, they literally form a single point. Step 1 triggers. We move right, printing that absolute center number, the 5. Then our top boundary pushes down, updating from 1 to 2. And because top is now 2 and bottom is 1, they finally crossed. The master loop cleanly terminates. Let's review the exact output of that mechanical winding path. If we string the whole sequence together, we get 1, 2, 3, then down for 6, 9, left for 8, 7, up for 4, and finally zeroing right in on the center with 5. A perfect, uninterrupted spiral. So, we've just conquered the 3x3 grid using this highly visual algorithm. But before we wrap up, I want to leave you with a thought to really test your newly established mental model. We used a perfect square today. How does this specific closing walls logic hold up if the matrix you're traversing isn't a perfect square, say a 3x5 grid? Think about those inner loops and those crucial safety checks we discussed. Grab a piece of paper, map out a rectangle on your own, and see what happens. Thanks for joining me for this explainer. I hope it helped lock this algorithm into your mind.
Now let's see how the code looks in C. in Java. In Python. Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes.
Hey everyone.
Thank you for watching. See you in the next video.
Subscribe now.